Hello. So in set 7, we did one problem today, and I was planning to do this problem tomorrow. And now I don't see you tomorrow. And so we're going to lose a little time together. So I'm going to ask you to complete this problem on your own with me talking you through it. So here we go. So the objective here is learning to use Newton's second law and free body diagrams to approach problems. So let's take a look at what we got. Two forces, F1 of 42 newtons and F2 of 22.5 newtons, act on a 5 kilogram block as shown. What's the horizontal acceleration and what's the normal force? Okay, so we're going to start by drawing a new free body diagram because I do not like how these arrows are pointing inward. It's conventional to have our arrows pointing away from the object. So I'm going to redraw this diagram over here on the left. So I normally start with the weight straight down, call that guy mg. We also have F1, which is pointing down. So we know that that's 65 degrees from the horizontal. Okay. We have an applied force F2 to the left. And then the largest force of all is that normal force from the table acting upward. I know that's large because it has to not only fight the weight, but also has to compensate for that y component of F1. So this isn't to scale because I didn't want to draw over the words. That normal force is going to be the largest of the four forces. Okay, so the first thing we have to do is figure out the acceleration. So to do that, we have to consider any force that has a horizontal component. So that force F1, I'm going to start off by breaking F1 into components. So it has an x component to the right and a y component down. Here's that angle theta. So F1x is adjacent to theta, so it'll be F1 cos theta. And F1y is opposite, so it'll be F1 sine theta. Okay, so those will come in handy soon. So in part A, to figure out the horizontal acceleration of the block, we'll write Newton's second law in the x direction for the block. And this first equation is always F equals ma. The second equation comes from the picture. So we don't know which, well, we could do a little math to figure it out, but we're not given which of the horizontal forces is larger, F2 or F1x. So I'm just going to assume that to the right is positive, and I'll just get started that way. If we end up with a negative answer, that just means that it's actually accelerating to the left instead. So I'm going to say the x component of F1 is working on the block towards in the positive x direction, and F2 is working on the block in the negative x direction. So now our goal is to figure out A, so you can set these equal and solve. All right, well, I know F1x is F1 cos theta. And so now I can plug in. Oh, I never wrote my givens. What the heck? So F1 is 42. Cos 65 minus 22.5 newtons all over the mass, which is 5 kilograms. So I plugged it into my calculator. I got negative 0.95 meters per second squared. So that means that the acceleration is to the left. I actually don't know which way this thing is moving. So it could be moving to the right and slowing down. It could be moving to the left and speeding up. We don't know. Part B is asking for the magnitude of the normal force acting on the block. So now we're going to change our focus to the y direction. So I am going to go ahead and say that the y acceleration is 0. We're not given any information to make me believe that this thing is accelerating vertically. In the positive y direction, we just have one force, that's the normal force, which is what we're looking for. In the negative y direction, we have two forces. We have the weight, and then we also have the y component of the applied force F1. So we're going to set these equal and isolate Fn. All right, add these to the other side. And expand that, F1 sine theta. Okay, so it was 5 kilograms times 9.8 newtons per kilogram plus F1, 42 newtons. Plug that in, I got 87.06 newtons. All right, so that's it. So we have a problem where we have an applied force that's applied at an angle, and we had to split it into its x and y components. We used the x part of the applied force to analyze what was happening horizontally, the y part to analyze what was happening vertically. And that's all there is to it.